right, welcome back. We're having a look at the probability and discrete distributions revision sheet. So let's start off with some really nice, easy probability questions. I've said that now. I probably won't be able to do them. Probabilities, like my least favorite part, and it was always my least favorite at school, but some people really excel with it. I think it's because you actually have to think it through and understand what's happening. Not my strongest suit. What's the probability that at least one of the runners will finish the race in under 10 seconds? The key here is at least. That's 1 minus the probability that none finishes. So it's 1 minus, well, 3/4, 5/6, and 3/5, which gives us 1 minus so it comes out as 5/8. So I'd say D is my solution. Could be wrong. Apologies if it is. All right, drawing pins thrown 400 times and fell point up 362 times. What's the relative frequency of the drawing pin falling point up and point down? Okay, so relative frequency for a large enough sample size is pretty much probability. So point up, we have 362 over 400. Which is 181 over 200. Did I need a calculator for that? No. And point down must be all the rest. So that would be 38 over 400, which is 19 over 200. Okay, point number B. What probability does this suggest for point up? P of point up. So this is suggesting that the probability of having it point up is 181 over 200, which is 0.905. And question C, the machine later repeated the experiment 1,000,000 times and the pin fell point up 916,203 times. So this is now saying P point up is 916,203 over 1123456, which is 0.916,203. Yes, this is a better estimate for probability. Because the sample size is far greater. Probability, let's think of it like tossing a coin. You toss it 3 times and it comes up heads every time. That suggests a 100% probability of getting heads every time. But we know it's not. So the more times you flip it, the more it'll tend towards the actual probability, central limit theorem, etc., as n is much greater. Okay. 50 tagged fish were released into a dam known to contain fish. Good. Later, a sample of 30 was netted from this dam, of which 8 were found to be tagged. Estimate the total number of fish in the dam just prior to the sample of 30 being removed. Okay, so the probability, the relative frequency of the fish in the dam, like it should be, the probability of getting a tagged one compared to the total should be the same. So from our sample, the probability of tagged, well, there were 30 fish that we pulled out and 8 of them tagged, yeah? So that's 4/15. Not a nice decimal. So 50 out of the total in dam technically should come out the same. So the total in dam should be over 50 is 15 over 4 times by 50, total equals 15 times 50 divided by 4, 187.5 fish. Okay, batch of 800 items is examined. The probability that a batch is defective is 0.02. Well, it's just 0.02 times 800. 16 defective. Not rocket science. A game involves, oh, I hate this question. 2 dice followed by rolling a third dice. To win the game, the number rolled on the third die must lie between the 2 numbers rolled previously. For example, if the first 2 dice show 1 and 4, then it's only 1 if you roll a 2 or 3 with the third. What's the probability that they have no chance of winning before rolling the third die? So they have no chance. Well, let's analyze. First, second. So if the first die is a 1, 2, 3, 4, 5, 6, and the second die is a 1, 2, 3, 4, 5, 6. They have no chance if they roll a 1, a 1, a 2, a 2, a 3, a 3, a 4, a 4, a 5, a 5, and a 6, and a 6. But they also have no chance if they roll a 1 and a 2. If they roll a 1 and a 3, you could get a 2 and you still have a chance. Okay, you have no chance if you get a 2 or a 1 or a 2 and a 3. A 3 and a 2 or a 3 and a 4. A 4 and a 3 or a 4 and a 5. 5 and a 4 or a 5 and a 6. Or a 6 and a 5. So that was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Out of our 36 combination options we had, which gives us 4 9s, I think. Hang on. Yep. Okay, what's the probability that they win? Just trying to think of. Like if they rolled a 1 and then a 3, the only way they could win is getting a 2. A 1 and a 4, they could roll if they got a 2 or a 3. 2, 3, 4, 2, 3, 4, 5. 3, 3, 4, 3, 4, 5. Wait. 2, 4, 4, 5. 2, 3, 3, 5. 2, 3, 4, 2, 3, 4, 5. 2, sorry, 3 or 4, or just 4. 3, 4, 5, 4, 5, 5. So the number of options we have here is 1, 2, 3, 4 options. 1, 1, 2, 3, 1, 2, 2, 1, 1, 3, 2, 1, 4, 3, 2, 1. So options to win. Was 10, 6, 4, 4, 6, 10. So 40 to win. Total dice combinations. Six for the first dice, six for the second, six for the third, which is 216. So the probability of winning is one if you get one of those 40 options out of the 216 options that could happen. Which is 5/27. Okay, good. It's a scary question. I'd hate to face that one in an exam. I would have put the star next to it and come back. Xavier's playing a variation of chess called Macrack online. Each game is graded and he begins with a 0.6 probability of winning and 0.3 of losing. At the end, he gets points, yada, yada. What's the probability that his first game ends in a draw? Well, that's fairly easy. 0.6, 0.3, it must be 0.1, which is 1/10. Okay, in the next game, after grading has occurred, Xavier now has a 0.4 probability of winning and a 0.4 probability of losing. Find the probability after 2 games, he gets this. Okay, tree diagrams are our friends. So let me just get some grid paper. We're going to have for the first, he could win, he could draw, he could lose. Actually, I'm going to really regret not giving myself enough space. Win, draw, lose. Okay. If he wins once, he could win the second. He could draw the second. He could lose the second, win, draw, lose, win, draw, lose. Now the probabilities for each one. For winning the first, it was 0.6, 0.1, and 0.3. But for the second, it's now 0.4 of winning, must be 0.2 of losing, of drawing, and 0.4 of losing. Now, this question specifically asks us about the number of points he's getting. So let's add up the number of points he'd get for each thing. If he wins, he gets 5. If he loses, he gets 2. And if he draws, he gets 3. So a win and a win is 10. A win and a draw would be 5 and 3 is 8. Win and a loss would be 5 and 2 is 7. A draw and a win, so 3 and 5 is 8. Draw and a draw, 3 and 3 is 6. Draw and a loss, 3 and 2 is 5. A loss and a win is 2 and 5 is 7. Loss and a draw, 2 and 3 is 5. Loss and a loss, 2 and 2 is 4. So the probability he gets 10 points, well, there's only one way for him to get 10 points. So it's just the 0.6 times 0.4, which is 0.24, which is 12/50ths. I don't know why they gave it to it in terms of 50ths. That's so weird. Okay, and P of less than or equal to 5, 5 points or less. Okay. 5 points or less, we've got draw and a loss, loss and a draw, and loss and a loss. So we've got 0.1 times 0.4, and we've got 0.3 times 0.2, and we've got 0.3 times 0.4. And we've got calculators. Gives us 11 over 50. Cool. For Jack to log on, he's got to put in the correct password. Unfortunately, he's forgotten his password. If he types the wrong password, he can make one more attempt. Probability of success is on any attempt is 2/5. Gosh, Jack, just get your life together. Assume that the result of each attempt is independent of any other attempt. Maximum 3 attempts can be made. What's the probability that he does not log on successfully? So not logging on successfully, the only way that can happen is that 3 wrong attempts. So we've got 2/5 times 2/5 times 2/5 comes out as 8 on 125. Not 8. Oh, that's success. So it's 3/5. Question B, calculate the probability that he logs on successfully. Okay, so the options we have are getting it right first. Two-fifths. Getting it right second. Well, we had 3/5 for getting it wrong the first time. Getting it right the second becomes 2/5. Getting it right third. I mean, this is much easier if I just, this would be so much easier if I just took that as the complement. 1 minus 3 wrong. So I've got 1 minus 27 on 125 gives us 98 over 125. A is 98. B is 125. All they wanted to do is write it as a fraction. Question C, calculate the probability that you logs on successfully on the second or third attempt. So the second, we had 3/5 for getting it wrong the first time, 2/5 for getting it right the second. So we've got 6 on, why did I have to do 6 on 25? The third time. We've got 3/5 for getting it wrong the first time, 3/5 for getting it wrong the second, 2/5 for getting it right the third. So that's 18 on 125. So together, we've got 6 on 25 plus 18 on 125 gives us 48 on 125. That's a VCA question. Yeah, I don't think they had a calculator for that question. 2-unit paper, yada yada. Probability of winning a game. Okay, so 2 colored dice. The blue dice has 4, 6, 8, 9, 10, 12. The pink dice has 2, 3, 5, 7, 11, and 13. They win if the number on the pink die is larger than the number on the blue die. Okay, so let's do up a table. So for the pink, they could have 2, 3, 5, 7, 11, 13. For the blue, they could have 4, 6, 8, 9, 10, 12. Let's do ticks for a win, crosses for a loss. The pink has to be larger than the blue. So the things 2, they've lost. The pink is 3, they've lost. Pink is 5, they've won if that's 4, but they've lost the rest. Pink is 7. We've won that one and we've won that one, but lost the rest. 11, we've won that one, that one, that one, that one, and that one, lost the rest. 13. So we've got 1 plus 2 plus 5 plus 6. Yes, I'm doing it on a calculator, don't shame me. 36 total options. So the probability of winning is 14 out of these 36, which is 7 on 18. Calculate the probability that they win at least once in 2 successive games. Winning at least once is the opposite of not winning at all. So we've got 1 minus, well, probably if we've got 14 36s for winning, 7 18s for winning, then we've got the opposite of that, we've got 22 on 36 of losing, and we've had to lose both games. (121/324) gives us 203/324. Class 30 girls, 13 dancers, 22 gymnasts. Seven girls do both, and what's the probability that they do neither? Let's draw up a Venn diagram. We know 7 do both. This is dance, gym. Okay, 7 do both, so that means we've got 6 that just do dance. We've got 16 that just do gym. 6, 7, 16 adds up to 29, which means we have 1 that does neither. 1 on 30 does neither. So it's C. Okay, this one again is going to be easiest if we do a Venn diagram. We're going to have French, Japanese, 28 students. All of them study at least one, so we have none doing neither. 28 students present, 18 do French and 22 do Japanese. So the probability of doing French is 18 out of the 28, which is 9 on 14. Again, why did I do that in my calculator? Probability that 2 randomly students both study French. Well, we've got the first one studying French and the second one studying French. 81 on 196. I'm really worried that I'm oversimplifying this. Like weirdly worried. Am I? It's question 8. Oh, okay. I've already chosen one of my students. Must be getting late. So we got 17 out of the 42 study both. Yeah, 17. Yeah. Anyway, probability that 2 randomly chosen students, 17 over 42, the probability that they study both languages. Okay, well, we know that we've got 18 in that group. We know that we've got 22 in that group. We know no one studies neither, so we know we've got 28. So 18, 22, subtract off the 28 will tell us how many did both. 12. So both 12 do both out of the 28 present. 3 sevens. Coin is tossed 3 times. What's the probability heads? Because half to the third equals 1 on 8. Okay. Zena and Gabrielle compete in a series of games. The series finishes when one plays 1, 2 games. In any game, the probability that Zena wins is 2/3 and Gabby wins is 1/3. Part of a tree diagram is shown. Complete the tree diagram. So we've got Zena winning the first game and the second. Zena winning the first game, Gabby winning the second. If that happens, then we do get a third game. Zena could win it, or Gabby could win it. Okay, second game. If Zena wins it, then it does go to a thirds. Again, Zena 2/3, Gabby 1/3. If Gabby wins it, it ends because she's already won 2 games. What's the probability that she wins the series? Well, the only probability we've got a few different situations. She could win the first game and the second. She could lose the first game and win the second and third. There's no other situation. Or she could win the first, lose the second, win the third. They're the only situations where I have her winning. So we've got a third times a third plus 2/3 times 1/3 times 1/3 plus 1/3 times 2/3 times 1/3. All up, that comes to 7 on 27. And the probability that 3 games are played in series is 1 minus the probability 2 games. So we've got 1 minus, well, the probability of 2 games was we had Zena winning both, 2/3 times 2/3. We also have Gabby winning both, so 1/3 times 1/3. So we've got 1 minus 4/9 plus 1/9. So it's 1 minus 5/9. So it's 4/9. Okay, packet of lollies, 5 red, 14 green, 2 lollies selected at random without replacement. Tree diagram. Okay, so the first could be red, could be green, probability of red, 5 on, what do we have, 19 total? Green, we've got 14 on the 19. Now it's just making me want lollies. Okay, and then again, we could get red. This time we've got 4 out of 18. Or we could have gotten green. This time we've got 14 out of the 18. Green, we could get red. We've still got 5, but we've only got 18. Green, we could get green again. This time we've got 13 out of the 18. So the probability of this branch, oh no, that's done. The probability that they're different colors, we've got red, green, green, red. This time we've got 5/19 times 14/18, and we've also got 14/19 times 5/18 gives us 2 lots of, because they're the same, 70 on 342 gives us 70/171. Again, nice, easy question. And they just say, okay, Kim's got 3 red, 2 yellow shirts on each of the 3 days. She selects a shirt at random. She wears each shirt and what's good. She gives them a wash. What's the probability that she wears a red shirt on Monday? 3 out of the 5. Hooray. And that was I. What's the probability that she wears the same color on all 3 days? Well, if she's only got 2 yellow shirts, so she can't be wearing yellow. She's got to be wearing the red. So we've got 3 out of the 5 for the first Monday, and then, but we've only got 2 left out of the 4 total. And then we've only got 1 left out of the 3 total. What does that come to? I don't know that I've been using my calculator, so I'm not going to not. 1/10. And what's the probability she doesn't wear a shirt on same color on consecutive days? Well, she could wear red, yellow, red, or she could wear yellow, red, yellow. So the probability of red, yellow, red, we've got 3/5, and then we've got 2 left, 2/4, and then we've got 2 reds left out of the 3 that are total. 1/5. Yellow, red, yellow, we've got 2/5, 3/4, 1/3, 1/10. So total, we've got this 1/5 plus 1/10 comes out as, let me just double check, 3/10. 2 machines produce pens. It's known that 10% of pens produced by machine A are faulty. 5% of the pens produced by machine B are faulty. 1 pen is chosen at random from each machine. What's probably that at least 1 is faulty? Well, that's 1 minus the probability that neither are faulty. Which means we've got 1 minus. Now the probability that the first one is not faulty is 95%. Probability that the second one is faulty is 90% and 95%. (29/200), which is 0.145. Coin is tossed to select one of the 2 machines. 2 pens are chosen at random from the selected machine. What's the probability that neither pen is faulty? So let's do a tree diagram. The first option they could have is choosing machine A. The probability of that is 1/2. Or they could have gone for machine B. Probability for that is 1/2. If they chose machine A, it could have been faulty or not faulty. It's faulty, that's 0.1, 0.9. Machine B, faulty or non-faulty, 0.05, 0.95. So the probability that neither is faulty is this branch and this branch. So we've got 0.5 times 0.9 plus 0.5 times 0.95 gives us 37 on 40. If we want that as a decimal, that's 0.925. Oh. Oh, 2 pens are chosen. So let me get rid of my highlighting. I didn't read the question. So if it's A, we could have 0.9 and 0.9. If it's B, we could have 0.95 times 0.95. Gives me 137 over 160, 0.85625. Okay, read the question. Okay. A bag with marbles, how original. It's got 1 green, 4 blue, 6 red. 2 are drawn from the bag with replacement. Find the probability that 2 blue marbles are drawn. Well, if the first one's blue, then we've got 4 out of the 1 plus 4 plus 6, 11. And if the second one's also blue, then we've only got 3 left out of the 10 marbles. So that gives us 12 over 110, which is 6 over 55. What have I done wrong? Oh, with replacement. We've left the marbles in the bag, or else it gets the hose again. For 11ths, that's 16 over 121. Again, read the question. This is usually a sign that I'm getting a bit tired. Probability that at least one of the marbles is red or green, that's 1 minus the probability that neither is red or green. And if they're not red or green, they must have both been blue. Which is 1 minus the 16 over 121, which gives us 105 over 121. Number 3. Single marble is now removed from the bag without noting its color, and it's replaced with a green marble. A marble is now drawn from the bag. What's the probability that it is green? That's a really interesting question. Let's consider the different scenarios. So the first scenario is the first marble was green. Actually, this can be easiest as a tree diagram, I think. Let's say the first marble they took out was green, which is a 1 on 11 chance. the probability that the second marble is green is still 1 on 11. If the first marble they took out was red, which is a 6 on 11 chance, then the probability of the second marble they take out being green, well, we had 1, now we've got 2 out of 11. And if the first marble they replaced was blue, which there was a 4 out of 11 chance, and they've replaced it with a green, then there's now 2 out of the 11 marbles being green. I don't have to consider the other branches, like these ones. I just have to consider this. So we've got 1/11 times 1/11 for the green being the first one, so there's green as the second. We've got 6/11 times 2/11 for a red being replaced. And we've got 4/11 times 2/11 for a blue ring replaced. I probably could have considered these two together, but I didn't. So all up, that gives me 1 on 121 plus 12 on 121 plus 8 on 121 gives me 21 on 121. Yes. Oh, yes. Okay. That's not a surprise. I was totally expecting to get that right. That was a mean question. Like, it wasn't terribly difficult, but getting your head around it. That's why I don't like probability. Okay. The spinner question. Show that the probability of player A winning first or second. Okay. So let's think of what happens. Player A so it's not the yardie, the player having the turn wins. Player having the turn loses. Okay, player B. Okay. They could land on an R, a P, or a Q. Then it's player B's turn. They could land on an R, a P, or a Q. I need to spread these out a bit more. And this is the first and second turn of the game, so I'm not going to keep going. If it stops on sector P, then the player having the turn wins. So for player 1 to win, they could get P straight away. These then disappear. Otherwise, if it had stopped on sector R, and then stopped on sector Q, then player A would have also won. So options for player A winning in the first two. Player A rolls an R, or player A rolls. Oh, and if they'd gotten a Q straight away, then player B would have won straight away. Rolls, sorry, not R, P. Player R, A rolls R, then player B rolls Q. Okay, it only keeps going if people keep rolling R's. Show that the probability of player A winning on the first or second is this. Now, the probability of rolling a P is P, sure. But then we've also got getting an R and then getting a Q. Okay. This doesn't have any Q's in it. So let's remember that Q is the same as 1 minus P or R. So we've got P plus R times 1 minus Q, P take R. So we've got P plus R take R, P take R squared. Which is the same as, oh, I think I'm on the right track. Let me just stash this to the side. If I rearrange this, that's P take R, P plus R take R squared. Okay, so P 1 take R plus R 1 take R, which is 1 take R P plus R. I don't know why they phrased the question like that. It was just like a really annoying algebraic challenge. Question 2, show that the probability that player A eventually wins the game is this. So for A to eventually win the game, they've got that branch. Like eventually winning. We've got P first up, and we've got R times Q if they won it the second time. Or they could have had R times P if they won it the third time. Or you could have had R times Q if they won it in the second. Oh, wait. Times R times Q. R times R times R times R times P. So this is winning on the first, second, third. To win on the third, they must have rolled R's must have been rolled in the other 2. To win on the 4th, R's must have been rolled in the other 3, etc. So we've got P plus RQ plus R squared P plus R cubed Q, R to the 4P, R to the 5Q, R to the 6P, etc. Yeah. Now Q is just 1 take P take R. So we've got P plus R times 1 take P take R plus R squared P plus R cubed 1 take P take R plus R to the 4th P plus R to the 5 1 take P take R plus R to the 6 P plus etc. Okay. Oh, I swear this is going to go somewhere. So we've got P plus R, take RP, take R squared, plus R squared P, plus R cubed, take R cubed P, take R to the 4, plus R to the 4P, plus R to the 5, take R to the 5P, take R to the 6, plus R to the 6P, plus etc. Okay, so we essentially have 2 geometric progressions. Now, we haven't done geometric progressions yet in class. I'm still going to work through this. This is your permission to stop. And I'm going to take P out. And I'm going to have 1 take R plus R squared, take R cubed, plus R to the 4, take R to the 5, plus R to the 6, etc. And then we're going to have just the R's on their own. 1 take R plus R squared, take R cubed, plus R to the 4, take R to the 5, plus R to the 6, etc. So we've got P plus 1 times 1 take R plus R squared, take R cubed, plus R to the 4, take R to the 5, plus R to the 6, etc. I'm really regretting deciding to do this question. Yeah, I'm going to leave it. We'll do that again at the end of the year. Okay, example 23. A game is played by throwing darts at a target. Player can choose to throw 2 or 3 darts. Darcy plays 2 games. In game 1, he chooses to throw 2 and wins if he hits the target at least once. In game 2, he chooses to throw 3 and wins if he hits at least twice. Game 1. To find the probability of winning, that's 1 minus the probability of losing, which in this case, he loses if he wins and he doesn't hit the target as well. Which means we've got 1 minus P is hitting the target. So for him to not hit the target, he must have missed the target, and it's happened twice. 1 minus, now 1 take P squared is 1 take 2P plus P squared. So 1 minus 1 is 0, 2P take P squared. Okay, aye. Game 2. probability that he wins game 2. He's got to hit the target at least twice, which means he can hit it once or twice. I mean, hit twice or 3 times. To hit twice, we've got, I'm going to do a tree diagram. This is confusing me. I need dinner. Hit, miss, hit, miss. If he hits twice, he won't throw again. Hit, miss. If you miss the first one, hit, miss. If he misses twice, he can't hit twice. Hit, miss. Yes, looks great. I know. So he could hit, miss, hit, miss, hit. There is only options. So we've got p squared plus p times 1 take p times p again, plus 1 take p for missing the first time, and then p squared for the next one. So we've got p squared plus p squared take p cubed plus p squared take p cubed. So we've got 3 lots of p squared take 2 lots of p cubed. I prove he's more likely to win game 1 than game 2. So we're trying to prove 2p take p squared is bigger than 3p squared take 2p cubed. Well, we know p is between 0 and 1. Let's get everything over to the left. So we've got 2p cubed take 4p squared plus 2p is bigger than 0. So we've got p outside of 2p squared take 4p plus 2 is bigger than 0. What exactly are we after? Oh, I'm right on the right spot. Oh, of course, I could have taken the 2 as well out as well. P squared take 2p plus 1. So we've got 2p times, this is the same as p take 1 squared. We know p is between 0 and 1. So this is positive and this is positive. So true. Okay, that's all we had to show. And then IV4, sorry. Find the value of P for which Darcy is twice as likely to win game 1 as he is to win game 2. So we're trying to say that 2P take P squared is 2 times 3P squared take 2P cubed. So 2P take P squared equals 6P squared take 4P cubed. So we've got 4P cubed take 7P squared plus 2P equals 0. So we're trying to find the actual answer for P. Let's take P out the front. 4P squared takes 7P plus 2 equals 0. So P equals 0, or 4P squared takes 7P plus 2 equals 0. Let's quadratic formula this. P equals minus B, so minus -7 plus minus the square root. Oh, we could have PSF, whatever. -7 squared, take 4 times A times C all over 2A. And I'm going to chuck that in my calculator. So we've got 7 plus minus root 17 on 8. Now we know 0 is less than P is less than 1, so check. Let's make sure that these answers are between 0 and 1. So 7 plus root 17 on 8 is too big. And let's double check the minus one. Yes, that's fine. So P must be 7 take root 17 on 8, or P must be 0. They're the two answers. The 7 plus root 17 on 8 doesn't work. In a certain population, 35% have blue eyes, 15% have blonde hair, 10% have blue eyes and blonde hair. Persons chosen from this population at random. Find the probability they have blonde hair given they have blue eyes. So this is definitely a given question. So the probability of A given B is the probability of having both. Yes. Divided by the probability of just having the second. Let me double check that I've got that formula correct. It's on your formula sheet. Oh, A and B. Yeah, sorry, I had my thing around the wrong way. Okay, so the probability of having both in this situation is 0.1. We're given that they have blue eyes, so we're just after the 0.1 from that 0.35. Gives us 2/7, which is 0.29. Question B, the probability they have blue eyes given blonde hair. So this one's the other way around. So we've got 0.1 over 0.15. 0. Sorry. 667. Yeah. This one, on the other hand, 2 boxes contain 4 stones. Box 1's got 4 black. Box 2's got 2 black, 2 white. box is chosen randomly, one stone is drawn randomly from it. Each box is equally likely to be chosen, as is each stone. What's the probability that the randomly drawn stone is black? Well, this might be easy to do as a tree diagram. So box 1, box 2. Box 1, the probability of getting that is 0.1/2. Let's do 1/2. Box 2, 1/2. Probability of getting black is 1 out of 1. It's 100%. They're all black. For box 2, the probability of getting black was 2 out of the 4. So we've got 1/2 times 1 and 1/2 times 2 out of the 4. Totally comes to 3/4. It's not known from which box the stone has been drawn. Given that the stone drawn is black, what is the probability that it was drawn from box 1? So the probability that it's from box 1, given that it's black, is the same as the probability that it's box 1 and black over the probability that it's black. So the probability that it's in box 1 and it's black is just this one. So the probability that it was from box 1 and it was black was 1/2 times 1. The probability that it's black overall is 3/4. 1/2 divided by 3/4 comes out as 2/3. Okay. For events A and B from a sample space, probability of A given B is 1/5. Probability of B given A is 1/4. Probability of the A and B is P. Find probability of A in terms of B. So probability of A given B equals the probability of A and B over the probability of B. The probability of B given A is the probability of A and B over probability of A. So if we want the probability of A, then we've got to do the probability of A and B over the probability of B given A. If we just rearrange that formula. So the probability of A given B is P. The probability of B given A, sorry, A and B is P. The probability of B given A is 1/4. So we've got P over 1/4. So the probability of A must then be 4P. Question B. Oh, the complement. So it's the probability of not in A and not in B. So if I actually draw this, and a lot of these, they make a bit more sense if you draw them. Let's say this is A and this is B. If the yellow is A, this is really laggy. The yellow is A, and I make the red everything not in A. Yeah, I'm trying to color this in and it's really laggy. Okay. So the red is everything not in A. If I color in B as light green, let me make that blue. Oh, this is really struggling. B is blue. Then you can see that this bit, the green, is a intersection B. So that's the stuff in both. If I color in the stuff that's not in B, in purple, then we're after the stuff that's both red and purple. And the only bits that are both red and purple, because the yellow's got no red, the blue's got no purple. The only bit that's both yellow, both red and purple is everything outside of whatever's in both. I mean, whatever's in either. So you can see by coloring it in that we're just after the outside of the whole thing. Okay, so we want the stuff that's not in either. So the probability of not being in that in A and not being in B is 1 minus the probability of being in either. The probability of being in either is the probability of being in A plus the probability of being in B, but we've counted the overlap twice, so we've got a minus the overlap. Now we know the probability of being in A, it's 4p. The probability of being in B, we can get the same way. It's the probability of A intersection B over the probability of A given B, which means we've got P over, and A given B was 1/5, which is 5p. So we've got 4p plus 5p minus the probability of being in that intersection. They told us was just p, didn't they? Which means we've got 8p. Which means the probability of being in neither is 1 minus 8p. Okay. And for question C, given that A union B, so probably being in either, is less than or equal to 1/5, state the largest possible interval for P. So we know 8p is less than or equal to 1/5. So we know P is less than or equal to 1/40. So we know 0 has to be between P has to be between 0 and 1/40th. Yep, which is what they got. Okay. Oh, we're close. We're close, guys. We've got the egg question. I don't know how many more we have after this. An egg marketing company buys its eggs from farm A and farm B, pays the amount from A, the rest are from B, yada, yada. 3/5 from farm A have white eggshells, 1/5 from farm B have white eggshells. Find the probability that the egg we've chosen has a white eggshell. Let's tree diagram this. So we could get it from farm A. The probability of getting from farm A is P. Once we've got it from farm A, it could be white, which is 3/5, or it could be not white, which is 2/5. Or else we could get it from farm B. If the probability of farm A is P, then this must be 1 minus P. If it's from farm B, probability it's white is 1/5. Probability it's not white is 4/5. Total probability that we're going to get a white egg is a white egg from farm A or a white egg from farm B. So we've got P times 3/5 plus 1 minus P times 1/5. So we've got 3P on 5 plus 1 take P on 5. So we've got 2P plus 1 on 5. Question B, another egg selected at random. Given that it has a white eggshell, find, in terms of P, the probability that it came from B. So we know probability of having a white is 2P plus 1 on 5. We want P that it's from B, given that it has a white eggshell. Well, that's going to be the same as the probability that it's from B and it has a white eggshell divided by the probability that it has a white eggshell. The probability of being from farm B and having a white eggshell is 1/5. The probability of having a white eggshell is 2P plus 1 on 5. So we've got 1/5 divided by 2P plus 1 on 5. So we've got 1/5 times 5 on 2P plus 1 gives us 1 on 2P plus 1. What have I not thought through? Oh, this isn't just 1/5. It's 1 take P times 1/5, which means I've got 1 take P on the top here. Which means I've got 1 take P on 2P plus 1. Because this is this whole branch, and I was just considering the second part of that branch. Okay, that's question I. Find the probability that this egg came from, if the probability that it came from B is 0.3. We know 0.3 is 1 take P. What? Oh, we already know that has a white eggshell. Excuse me. So we know 1 take P over 2P plus 1 equals 0.3. And that's what they're getting us to solve, presumably. Okay. So we have 1 take P equals 0.6P plus 0.3. P's on the left, other numbers on the right, we've got 0.7 equals 1.6p. So 7/16 equals p. Yep. Okay. We're up to the second part of this unit. Okay, number showing that's numeric discrete, because you can't have a 1.7 showing. The weight of a randomly chosen male, definitely numeric, definitely continuous. Rains or not, we're not saying how much it rains, we're just saying if it rains or not, so that's categorical. Daily rainfall in Sydney, so this time we're taking numerical and it's discrete. Color of a ball, that's definitely categorical. Colors of two balls drawn together, that's definitely categorical. Shoe size, look, it's numeric. It could be discrete or continuous, whether you regard like 40, 41, size 9, size 10, size 11, or if you consider size 9, 9.5, 10, 10.5, like you could argue either way. ATAR results, it's definitely numerical and it's definitely continuous. Oh, they're saying discrete. Oh, I guess you can't get 97.87625. It's 2 decimal places. Okay. So if we're choosing 2 pairs at random, we could have 0, 0, or 1, 1, or 2, 2, or 3, 3. So we could have 0.5 squared. We could also have 0.25 squared. We could have 0.2 squared, and we could have 0.05 squared. All up, that comes to 71 on 200, which is 0.355C. Okay, 4 coins are thrown, number of heads is recorded. Probability of getting 0 heads is 1/2 to the 4. (1/16). Probability of getting 1 head, like all of these are getting 1 head. We've got that option, or we could have that option, or we could have that option, or we could have that option. So there's 4 options that have exactly 1 head, so 4/16. 2 heads, better than 1, I guess. Head, head, tails, tails. Head, tails, head, tails. Head, tails, tails, head. Tails, head, head, tails. Tails, head, tails, tails. Wait. Tails, head, tails, head. Or tails, tails, head, head. So that was 1, 2, 3, 4, 5, 6 options. Getting 3 heads is the same as getting 1 head. So that should also be 4/16 and then 1/16. Let me double check. 1 + 4 + 6 + 4 + 1 is 16. Good. Probability of getting 3 heads is 4 on 16. Greater than 2 heads is 4/16 plus 1/16, which is 5/16. And odd number of heads is 1 and 3, so 4/16 plus 4/16, 8/16, which is half. Okay. A die is thrown. Write out the probability distribution for the number shown on the die and graph the distribution. So we've got X, we've got the probability that the number of things we roll is equal to that. Now we could roll a 0, sorry, of 1, 2, 3, 4, 5, 6. Probability for each of these is just going to be 1/6. So if we do a nice little graph, here's the probability. Here's what you could get. You could get 1, 2, 3, 4, 5, 6. Doesn't matter. It's always just going to come out as a 6. Consider the following discrete probability distribution for the random variable. The mean is what? Well, let's start off by trying to find P. We know all these probabilities have to add up to 1. So we know P plus 2P plus 3P plus 4P plus 5P equals 1. So we know 15P is 1, so P is 1 on 15, which means the mean, it's X times the probability plus X times the probability plus X times the probability, etc. So let's do that. We've got 1 times P plus 2 times 2P plus 3 times 3P plus 4 times 4P plus 5 times 5P. So we've got 1 plus 4 plus 9 plus 16 plus 25 gives us 55P. So we've got 55 times 1 on 15, which gives us 11 on 3, which is D. This one, we need to find the mean before we can find the probability that we're less than the mean. So the mean is 0 times a quarter plus 1 times 9/20 plus 2 times 1/10 plus 3 times 1/20 plus 6 times 3/20 equals 9/20, 1/5, 3/20, and 9/10 gives us 17 on 10. So the probability, which is 1.7. So the probability that X is less than 1.7 is, well, we've got the 1/4 if we rolled a 0, and we've got the 9/20 if we rolled a 1. And we can't go to the 2 because that's already more than 1.7. So we've got 1/4 plus 9/20 gives us 7 on 10, which is E. Okay. Oh. E of X is the mean, by the way. So we know A plus B plus B plus 2B plus 0.2 equals 1, yeah? So I think this is going to be easiest if we write A in terms of B. So A plus 4B is 0.8. A is 0.8, take 4B. And then the expected value of X is minus 1 times A, which is 0.8, take 4B, plus okay, I'll keep going. 0 times B plus B times B plus 2B times 2B plus 4 times 0.2. So we've got negative 0.8 plus 4B plus B squared plus 4B squared plus 0.8. So the expected value is 5B squared plus 4B. Now, B has to be between 0 and 1. That's not helping me. But also, A has to be between 0 and 1. And I know A is 0.8 take 4B. So A realistically tops out at 0.8. When A is 0.8, B is 0. When A is 0, 0 equals 0.8, take 4B. B equals 1/5, which means the expected value of X when B equals 1/5 equals 5 times 1/5 squared plus 4 times 1/5. Which should just come out as 1. The expected value of X when B equals 0 is 5 times 0 squared plus 4 times 0, which is 0. So E of X is between 0 and 1. It's a lot of work for 1 mark, which is E. Okay, damn, Daniel. Let's find the mean. You could just smash this out on the calculator. I'm not going to. We've got 0 times 0.2, 1 times 0.2, 2 times 0.5, 3 times 0.1 gives us 1.5. Probability that he receives only 1 telephone call on each of the 3 consecutive days. Well, we've got the 0.2 for each day. Comes to 0.008. He receives telephone calls on both Monday and Tuesday. what's the probability that he receives 4 calls over these 2 days? So the probability that he gets 4 calls given both Mon and Tues is going to be the probability that he gets 4 calls and both Mon and Tues over the probability of getting calls both Mon and Tues. I've written that and it looks great, but now I can't remember what to do. So the probability of getting 4 calls on both Monday and Tuesday is he could have gotten 1 and then 3, 2 and then 2, or 3 and then 1. So that gives us 29 over 100. The probability that he actually gets calls on both Monday and Tuesday is 1 minus the probability of no calls. So it's 1 minus 0.2 times 0.2. So it's 24 out of 25, which means the probability of 4 calls given both Monday and Tuesday is going to be 29 over 100 divided by 24 on 25. $29 on 96, but they got 29 on 64. I'm Googling. I've already Googled this question. Oh, this feels like failure. Which question was it for? I think I was trying to be really fancy with this one because this is where I went wrong. Probability of getting calls on Monday and Tuesday. Well, they could have 0.8, 0.8, which is 0.64. So it becomes 29 over 100, which is 64. 100 over 64. 100, which then gets us 64 on the bottom. I don't know what I was on about there. No, yeah, I don't know. Anyway, this one, the variance. Now I'm going to have to look up the formula. I can never remember it. Hopefully you can. is the expected value of the value minus the mean squared, which is the same as the expected value of x squared minus the mean squared. Okay, so let's figure out the mean. We've got -1 times p plus 0 times 2p plus 1 times 1 take 3p. So it's -p plus 1 take 3p. So it's 1 take 4p. I'm going to do a new table. Actually, I'm just going to add up my own row. Oh. So if I add a row for x squared and I try and figure out the expected value of x squared minus the mean squared, that means that I'm doing, instead of -1 times p, it's going to be -1 squared. So 1 times p plus 0 squared was 0 times 2p plus 1 squared was 1 times 1 take 3p. So in this situation, we had 1 take 2p. So that's the expected value of x squared. The mean squared is 1 take 4p squared, which is 1 take 8p plus 16p squared. So the variance is 1 take 2p minus 1 take 8p plus 16p squared. Which gives us 1 take 2p take 1 plus 8p take 16p squared, gives us 6p take 16p squared, which is D. Yeah, this was the much easier version of that formula to use. Now you have actual numbers, so feel free to use your calculator. Yeah, I'm going to use my calculator. So we do mode, 3 for stat. We have 1 for single variable, but I forgot to make sure that my frequency column is on. Number 1, okay. So for x is 0, 1, 2, 3, 4. And now I'll go in and put the frequencies. So 0, 0.0, 0, 0.1, 0, 0.2, 0, 0.3, 0, 0.4. Okay, press on, shift stat 1. I want information about 4 variants. Okay. E of x is the same as x bar, which in this situation came out as 3. And the variance of x is sigma squared. So in this situation, it's 1 squared, which is 1. Okay, for my next table, we've got -2, -1, 0, 1, 2. Let's put in those probabilities as relative frequencies, 0.3, 0.1, 0.2, 0.1, 0.3. Okay, on number 4, 3, oh, sorry, 2. I got an X bar of 0. Oh, here standard deviation was 1. Standard deviation for this one is 1.6, which means the variance is that squared, which is 2.6. And that's it. Well done. That was a big topic. Yeah, that was a weirdly huge topic. See you next time on more Adventures of Year 11 Mathematics Advanced.